So you're in the middle of the huge sea of organic reactions and you're getting a little nervous because it's a little stormy. Well, this video will help you stay afloat by teaching you all about oxidation states. I want to emphasize that a written tutorial is also available to amplify the material in this video on the Canvas site. So let's get going here. What is redox anyway? Well, redox is all about electrons, and basically you give electrons, you are reducing something. If you take electrons away, you're oxidizing something. But in O-Chem it's a little bit different. We really like to focus on the atoms that are associated with those electrons. And so, for example, when we look at the electron source of these pi systems, these pi functional groups, alkenes and alkynes, when I think reduction, I'm going to think about the fact that I'm adding hydrogens to my substrate. So I went from H2 on each carbon to H3 on each carbon. And that's a pattern we're going to see over and over again, that a reduction adds hydrogens. So for example, when we look at the alkyne, we can add again a pair of hydrogens, and that goes from the alkyne to the alkene, gone from 2 hydrogens to 4 hydrogens. And in fact, if you think about it, we can reduce again. We can reduce the alkyne all the way down to the alkane by adding H2 twice. So the take-home message here is that reduction in O-Chem is addition of hydrogen. Well, what about oxidation? Well, that's even easier. In O-Chem, oxidations are adding oxygen. So I can go from my pi system, my alkene, and, for example, turn it into a diol as shown. That's an oxidation. And I could even go from an alkyne to this kind of funky looking dicarbonyl. That too would be an oxidation. And what you should probably also notice is that in effect an oxidation could be considered taking hydrogens away. Alright, so how does this help us? Well, we're going to learn about oxidation states, and oxidation states will definitely tell us what kinds of reagents to use. So before we get started on oxidation states, let's do a little quick review. This is really a review from Gen Chem. If you were given, say, iron trichloride and asked to assign the oxidation state of the iron, that's pretty easy. All you have to do is kind of take off the chlorine atoms, and you're taking them off with a pair of electrons because, of course, you know that they are Cl minus, chloride anions that are coordinated to your iron. Well, since your iron trichloride overall has no charge, it's a neutral compound, we now know then by simple math that this iron has to have a +3 charge to balance out the 3 times -1 negative chloride anions. So you're looking at what's attached, adding up the charge, -3, and since the whole thing is neutral, that means the iron must be +3. Well, we're actually going to do that in O-Chem as well, but before we do, let's just focus in on how knowing reduction or oxidation helps us. If I know I'm reducing my functional group by adding hydrogens, that means I know I have to use a reducing agent. And we'll see in chapters 19 and 25 that there are some pretty common reducing agents. And the nice thing is, reducing agents, I hope, make sense. Hydrogen, and this is more of a Gen Chem kind of reducing agent, but if you have a metal that is in the zero valent state, something say like zinc or maybe tin, well, you know that these zero valent metals really like to get oxidized. Say zinc likes to go up to zinc +2, or tin can go all the way up to tin +4. So any metal that's in a zero valent state has a lot of electron density, and it can happily donate those electrons to be oxidized. That means whatever it's reacting with is going to get reduced. So those are our typical reducing agents. How about oxidizing agents? Well, they're really simple and straightforward too. What do you see? What do you notice? Oxygens, 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 oxygens. Holy schmoly. Wow, we've got so many oxidizing agents, we've got ozone in there twice. So, reducing agents are either hydrogen donors, hydride in particular, or a zero valent metal. Oxidizing agents are things that have lots of oxygens on them and are typically in a high oxidation state. So that's chromium +6, manganese, what is that? I think that's +7. And so you're looking for metals on this side that are really in a high oxidation state. All right, so what about this whole oxidation state thing? Well, we already talked about it with iron trichloride. How is it different in organic chemistry? Well, the thing that's different about organic chemistry is, of course, that we're now talking about covalent bonds, not ionic bonds. So the ionic bond is easy. It's an ion. We took off the chloride as an anion, leaving behind the iron as a cation. Well, we can't do that in O-Chem because they're not ionic. But we can pretend, and that's exactly what we do. We arbitrarily assign oxidation states to various atoms, like the heteroatoms, oxygen and nitrogen, maybe a halide, or a hydrogen. And we kind of think about the electronegativity difference in the polar bond between the carbon and that atom. So, for example, if we think about a carbon-chlorine bond, we know that that's a polar bond and that chlorine is going to have more of the electron density. So we artificially assign a Cl or a bromine or a fluorine or any of the halides a -1 oxidation state. So that means that if we're going to look at something like carbon tetrachloride, we're going to think of that as carbon +4 and 4 Cl minuses. So the oxidation state on that carbon is +4. All right. Now, carbon isn't, these are not ionic bonds. Carbon doesn't really have a +4 charge on it, but assigning these oxidation states and looking at the change in oxidation states in a chemical reaction helps us determine what kind of reagents to use. And we'll get through some examples here in a minute. All right, well, what about something like maybe an alkene here? How do we assign the oxidation state for that carbon? All right, well, the electronegativity difference between carbon and hydrogen is pretty insignificant, but we say that hydrogen is like +1, and because there's essentially no electronegativity difference between carbon and carbon, right? Then we give a carbon attached to another carbon an oxidation state value of 0. So for me to assign an oxidation state to that carbon right there, what I'm going to look at are the quote-unquote 4 things attached to that carbon, because of course carbon always has 4 bonds. Well, it's attached to a hydrogen, a carbon, and a carbon, because these two are the double bond. Well, hydrogen is +1, +1, 0, 0. So the charge total on the things that are attached to that carbon is +2. Well, I know the darn thing is negative, so the oxidation state of that circled carbon is -2. We'll do one more example here, looking at, say, how about an alkyne and we'll just put a phenyl group there just to ignore that. I am interested in that carbon's oxidation state. So it's got a +1 attached here from the hydrogen, and these are all 0. So for me to assign the oxidation state for that carbon, this is going to have to be a -1 to make the whole thing neutral. Alright, let's wrap this up with a couple more examples that it will illustrate how knowing the change in oxidation state helps you to determine what reagents to use. Alright, so here's an example where we're going to add hydrogen across a double bond to go from an alkene to an alkane. Let's prove that the oxidation states show that this is a reduction. So the first thing I'm going to do is get rid of the dang line structure and put in all the atoms here. Alright, so there's my alkene. And what I can see is that for this carbon right here, we'll circle it, I have a hydrogen attached, a carbon, a carbon, and a carbon. So this is +1, so that means my overall oxidation state for that carbon is -1 because the other carbons are all contributing 0. And since this is symmetrical, I know that the oxidation state on the other carbon is also 0. Now why am I interested in those two carbons? Well, because that's where the change is taking place. I'm going from CH to CH2. So let's prove that this is a reduction. And that should be pretty evident straight away, because now I've got +1, +1, looking at the oxidation state of this carbon or this carbon, because they're absolutely the same. +1, +1, that means this carbon has to be a -2. So I have gone in this reaction from an oxidation state of -1 to an oxidation state of -2. Therefore, this is a reduction. And we're using a reducing agent to carry out this reaction. Next example, what happens when I take cyclopentene and add something like potassium permanganate to it? Well, let's just again look at the oxidation state differences. We already determined from the previous slide that these are each -1. So what are the oxidation states for the affected carbons here? Well, remember, line structure is absolutely positively the enemy. So each of these carbons really looks like this. Again, it's a symmetrical molecule, so the oxidation state will be the same for each of these carbons. So I've got a +1 and a -1. Those two are going to cancel each other out, so the oxidation state for each of these carbons is 0. I've gone from -1 to 0. Therefore, this is clearly an oxidation. Alright, when I say I'm going from -1 to 0, that's focusing on only one of the carbons. If you look at the overall change in oxidation states, I have -2 going to 0 because we have two -1 carbons in the starting material. Alright, last example here. Let's look at an oxymercuration. Is this an oxidation or a reduction? Well, if you just look at the reagents, you might be led astray. So let's figure it out. -1 on the left. And what's going on here? Well, I've got one carbon that is going to have an additional hydrogen on it now, and one carbon that has been given an oxygen. So quick review, this was +1, +1, -1, +1. Alright, so that gives me an oxidation state of 0 here and -2 here. Well, -2 goes to -2. So this is neither an overall reduction or an oxidation. you can say that, yeah, that carbon was reduced and this carbon was oxidized, but when you take it as a whole, this is neither an oxidation or reduction. It's just a functional group interconversion. So I'll be using redox a lot in the mini lectures and in problems in class. So take a little time to review that tutorial on the Canvas page, get real comfortable with oxidation states, and we will see you in class.